All right, we're ready. Today we're doing another beam topic. This one is called design of beams, but it's really beam selection. So remember, we've got these beam charts. Let's look at the S chart. So S would be standard flanged I-beams. So an I-beam with regular size flanges on it, as opposed to a W, which would be a wide flanged I-beam. So let's look at these. Oh, see if we can get it to, there we go. So what we've got, we've looked at some of these pieces before where we've got the depth, meaning the, how tall is the beam. And notice the S24, that 24 is the nominal depth, or you might call it height. And it's actually 24.5 for this particular beam. Width means, in this case, width of the flange, thickness of the flange, the web. So in an I-beam, that middle part between the two flanges is called the web. On a T-beam, that same kind of piece is called the stem. Then we've got these two sets of information about axis XX and axis YY. So if you notice on our little picture up here that they gave us, the XX axis is shown horizontal, YY is shown vertical. How you decide which one to use is which one is parallel to your neutral axis that you're dealing with. So XX is most of the time going to be the one you're using. It could be if your loads were coming in from the side, or maybe the beam is turned on its side, then maybe you would use the YY axis, but pretty much most of the time for what we're going to do, you're going to use this XX. And we looked under there and we had I, but we had these other things. We have R, we don't really need that one for anything we're going to do today, but we have this S. So S is called the section modulus. So if we go back over here, we had an equation for calculating, oh, hold up. Yeah, that was going to be annoying if I had the touchscreen on trying to write on it. So we had a flexural stress equation. And we've used it a couple of times to calculate maximum flexural stress in a beam, things like that, but it was sigma equals, and technically there's a negative sign the way we're using this equation, m times y, sometimes there was a c in that spot, over I. Okay, and when we said, well, we want to know sigma max, that's when we did m times c over I. And maybe or maybe not, we put the negative sign, depends on if we were keeping track of it or not. But there would be a little negative sign there. Because C is, well, let's talk about Y. Y is the distance from the neutral axis to some point on the beam. So if we had an I-beam, well, let's do a rectangular beam. So there's our beam cross section. And we know that it has a neutral axis right through the center of it. And if we want to calculate the flexural stress at some point on the top of the beam, then we would measure from that neutral axis up to that point, and that would be Y. If we wanted to do the same thing on the bottom of the beam, we would measure from the neutral axis down to that point, which would be Y. When those points are the furthest away from the neutral axis that you can be for that beam, then a lot of times you use C. So C is telling you that you want the largest possible stress. So the largest possible distance from the neutral axis, because it's in the numerator, so the bigger the number you put in there, the larger you will calculate, and this number that you're calculating is flexural stress. So MC over I. Then you look at it, and C and I, those are both dependent on the cross section. So you've got the moment of inertia in the denominator there, that is dependent on the shape of the cross section, and you've got C in the numerator, which is also dependent on the cross section, at least how tall it is. So both of those are related to the shape of the beam, and so you can combine those together. So you combine into this variable called S, the section modulus. And that's the number that's in our little chart here, S. And you have one for the XX version and for the YY. There's a SS, or well, there's a S in both of those sets of numbers. And how you combine them, you don't just like add them together or anything. S equals I over C. So anytime that you're trying to do some maximum type thing, because it is C in there, so it is the maximum flexural stress. Anytime you're trying to do that, you can write sigma max. I want to drop the negative sign off of this, and you just have to know. The negative sign is there telling you if it's tensile stress or compressive stress. And so if you can just look at the beam and tell if it's tension or compression, then we don't really need the negative sign. So we could just say sigma max equals M over that section modulus S. And now, if we know that, we could write this as R. S equals sigma max over M. Technically that's M max, the maximum bending moment. If we're trying to do this maximum stress, we should find the maximum bending moment also. So what I can do here is I can say, well, another way I could look at this is if I have an allowable stress. So I know how much stress I want to allow to exist in the beam. So maybe I have sigma allowable equals some kind of sigma max divided by a factor of safety. So that's factor of safety. So it might be like factor of safety of 2 or something like that. And sigma max might be some material property that you look up in a chart. And if I know those kind of things, then what I can do is I can back out. If I know how much stress I'm going to allow, I know the maximum bending moment. Maybe I drew the shear and bending diagram. So I know the maximum bending moment to expect. Then I can back out the section modulus that I need in order for that beam to not fail due to my criteria here. So it might be, let's just say, let's do a sample one without all of the stuff around it, but let's just do this. Let's say that we have a S beam, so we don't know which one, with a factor of safety. I'm just going to do this factor of safety. Factor of safety equals 2 against yielding. And let's say the maximum bending moment equals, we've drawn the shear and bending diagram, and the maximum that we came up with was 15 kilonewton meters. Actually, I think the chart I have pulled up is US units. Yeah, so let's not do kilonewton meters. Let's do, I don't know. Well, let's just do 15 kip feet. So a kip is 1,000 pounds. So that's 15,000 foot-pounds. So we've got our factor of safety. We're going to assume that this is structural steel. So what we want to find is the minimum and I'm using minimum here to mean minimum weight. Because in general, a lighter weight beam is going to be cheaper. It's got less material in it, it's cheaper to move around, cheaper to put into place, you know, and everything about it's cheaper. Maybe not 100% true, but in general, the minimum weight is going to be the most affordable beam. All right, so this would be a pretty straightforward beam design problem. You don't have to go draw the shear and bending diagram. You're given all the relevant information and all that. We'll do one in a minute where we draw the whole thing out and calculate everything. But for now, we're just going to do a simple one. All right, so it's structural steel. It has a factor of safety of 2 against yielding. So if you don't remember the material properties, we do need to go look that up. So let's grab this material property chart. And there's our structural steel. We're in the right units. Tensile strength for this is 36 KSI. Compressive strength is B. If you go down to the bottom, it says B for ductile metals. You assume tension and compression properties are the same. So 36 KSI. We're not using the 66 because that's the ultimate strength. So our problem says factor of safety of 2 against yielding. So that means we want the strength where it's going to begin to yield, not the strength where it's going to fracture. So 2 against yielding means that our sigma max that we're going to have from our material, it said it was 36,000 psi, it said 36 ksi. And then our sigma allowable, we are only going to allow half of that. We have a factor of safety of 2. So sigma max. Well, let's put sigma y in there for yield strength so that we don't get it confused with the ultimate strength. Sometimes it might be that your factor of safety is against fracture, but most of the time your factor of safety is going to be against yielding because you don't want the part to permanently deform anyway. So most of the time your factor of safety will be against elastic strength, yielding, that kind of thing. But you could assign it against fracture if you wanted to, just for a test question or something. So our allowable stress is that 36,000 psi divided by our factor of safety, which is 2. So we're going to allow 18,000 psi of stress in our beam. Okay, now we go up to our equation for the section modulus, which says the section modulus that corresponds to this strength and this allowable stress and this bending moment is S equals, and we're looking at here, sigma max. In this case, it's sigma allowable over the M max that we put down right here. So sigma allowable over the maximum bending moment we expect is we're going to allow 18,000 psi, and we've got a uh-oh, did I put this backwards? Yeah, I did. I wrote those backwards. I was just looking at them and like, that's not going to do what I wanted to do. When I rearranged this equation for section modulus, I don't know, I just did it backwards, but it should be M over sigma, not sigma over M like I had written down. Yeah, let's do this the other way around. M max over sigma allowable. All right. So our maximum bending moment that we had, I forgot what it was now. 15 kip feet. So I'm going to convert that over to a couple of things here. So 15,000 foot-pounds, except that in sigma, my strength, there is pounds per square inch. So I don't want these feet over here. So I'm going to convert this. There are 12 inches per foot. So now I have inch pounds in the numerator, and that will work better with the pounds per square inch in the denominator. We said that our sigma allowable was 18,000 psi. So now the pounds will cancel out, the inches will all end up multiplying together, and I'll have section modulus in inches cubed. So let's see what number that is. 15,000 foot-pounds times 12 to get to inch pounds divided by 18,000 psi is 10. So 10, and the units on that would be inches cubed. All right, so what do I do with that number? That number means that the minimum section modulus that will satisfy this condition, I've got a factor of safety of 2 against yielding, made out of structural steel. It is a maximum bending moment of 15 kip feet, all of that kind of stuff. The minimum beam that will satisfy this and meet my criteria, particularly the factor of safety against 2, being made out of structural steel, has a section modulus of at least 10 inches cubed. So then I go to my chart here. Well, not that chart, the S chart, because I did say I wanted a standard I-beam. So I go to the S chart, and in general, the top of the chart has the largest numbers, largest beams, and as it gets smaller and smaller as I go down. So I've got to look in this column for S, so that's this one. And I do want XX. I didn't specify anything about the beam being loaded on its side or turned sideways or anything like that. So unless you have a picture that tells you that you're loading perpendicular to this y-axis, you're not going to use it. If you don't have any information, then you're assuming you're loading against the XX axis. So we need one. These are certainly work. 258. I only need 10. Some of these won't work. There's a 5 in there. Oh wait, that's the radius of gyration? Never mind. Here, 10.5. That looks like that one is the one that's lowest on the chart. Maybe not the right one, but the lowest on the chart. That would work. All of these 8.7s and 1s and all that, those are not strong enough beams. They would fail. They may not break in half, but they don't meet my factor of safety of 2. So those are too small. So what I do is I look, this 10.5 is a S7 by 15.3. So the S7 by, was it 15.3? Yes, 15.3. The section modulus for that was 10.5 inches cubed. So that number is greater than that, so it will work. So that's good. But we wanted the minimum, right? So this beam that we picked out so far, remember this number, that weighs 15.3 pounds per foot. So every foot of this beam that I cut off is another 15.3 pounds. So I need to go back and check if maybe there's a bigger beam up in the top of the chart, but it actually weighs less. So let's see. So I'm down here at the S7 by 15.3 and looking up, there's a 20, 18, 23, then they start getting really big. So it does look like the S7 by 15.3 is the best beam for this scenario that I've created here. So we would mark that down as our selected beam. You're not trying to get exactly 10. You're not trying to get as close to 10 as possible. This 10 is just the minimum section modulus to meet your design goals. Anything greater than that will work. And so once you find the beam that, or the set of beams that will work, then our criteria is going to say that we look for the lightest weight beam among those that will actually work for this situation. There might be some reasons why you don't pick that particular beam. You might have some height considerations where the beam has to fit within a certain height, and so that eliminates some of the bigger beams. That's not going to be in any of the problems that we assign, but it could be a thing that you encounter in real world. But anyway, we would choose this one. All right, so I'm not seeing any questions, so I'm assuming everybody's, there actually aren't that many people here right now. So if you have questions after the fact, then you'll have to let me know. We're going to work a pretty serious problem here. This guy. This one's overkill for what we would do on an exam. This is optional problem number 19, optional 2, number 19. So it's got a lot going on. I'm actually not going to solve the reactions for it. We're just going to grab these from the answers, and we'll go from that point. So let's copy this thing and work on it some. Let's get all of this. Okay. And we'll put that right here. All right, and let's go find the reactions for B and E. So they're right here. So they should be the first. So B should be 25.79. What are those units? Kilonewtons. Well, let's just do 25.8. I know that'll probably throw us off, but I don't want to deal with all these decimal places. So the reaction at B is 29.8 kilonewtons. The reaction at E, 30. We'll just do 3. That's probably not going to be okay for web work answers later on, but we should tell if we're close or not. All right, and we've got concentrated moments, distributed loads, point loads. We've got all kinds of stuff going on with this one. So let us label them, and then we'll draw our shear and bending diagram. All right, so M1 is 9.6. I'm going to have to leave the units off just to make things fit, but these are all in kilonewtons and meters, so we'll just have to remember that. W1 is 10.88. RB we just found 29.8. M2 3.2. W2 14.88. F 8.48. These are not convenient numbers, are they? W3 13.92. M3 9.6. And the reaction at E 30.3. All right, so we would have to go and lump all these distributed loads, do a moment about B or something, and find the reactions. We're going to skip all that. We're going to, this is on the beam design problem on the exam. It is more like what we just did. Well, where did we just do that? Up here. More like this, where you're given that. You might be given a picture of a shear and bending diagram and have to basically go find, the maximum moment from that picture. But I'm not going to make you draw the shear and bending diagram and then draw or then calculate the best beam section modulus from that. If you have, maybe we should take a little aside real quick. There are a couple of beam types where if you have a certain scenario, then you don't have to draw the shear and bending diagram to know where the maximum bending moment is. So one of those is a cantilever beam. So cantilever beam, maximum bending moment is always here at the wall. So you don't have to go draw the shear and bending diagram if you have a cantilever, because you know the maximum bending moment is at the wall. is probably negative unless the beam is being pushed upwards, but that's still the maximum magnitude. For simply supported beams, there are still a couple of little things where, as long as you've got symmetry, so if I had a axis of symmetry right here between the loads, the supports, everything, they don't have to be a pin and a roller, but two supports of whatever kind, two rollers, two pins, a pin and a roller. As long as everything is symmetric, the loads, if I have a point load over here, I've got the same point load over here. If everything's symmetric, then the maximum bending moment is at the center. So those two scenarios will speed up things if you happen to run into one of those, as far as trying to figure out where the maximum bending moment might be without having to draw the whole diagram. You can draw the diagram and you'll find it that way too. It will just speed things up if you know that. All right, so that's just a little bonus thing. Let's draw this one. This is definitely not either of those cases. It has a cantilevered section right here, AB, but it definitely doesn't have symmetry. So it's going to be one where we have to draw the shear and bending diagram. All right, let's draw our little guidelines. So I'm going to put one here, and we'll put one here. Oh, I didn't put my dimensions for the X direction on here. Got this one. I need one here. That's where the distributed load changes, plus there's a point load there. And one here. And then we'll have our 0 line right here. All right. So that'll be shear equals 0. The units for shear on this are kilonewtons. Okay. And we need to put in A, B, C, and D. Let's see. A is 1.1 meters. B is 2. C is 0.9. And D is 1.6. Let me find my calculator. We're definitely going to need that. Here it is. So it looks like the concentrated moments, the M1, M2, and M3, they don't do anything in the shear diagram, so I kind of ignore them for now. But it looks like I'm going to have something that goes down. Then I'm going to have the reaction at B going up. So I'm not going to get much outside of maybe 30 or so kilonewtons. So I'm going to count by tens. So we'll have 10, 20, 30. And then we'll have negative 10, negative 20, negative 30. Okay, we start at 0. And then the first thing that happens is, now I'm missing the fact that I didn't lump these distributed loads together. So let's do that real quick. The units on this 10.88, that is 10.88 kilonewtons per meter. So 10.88 times 1.1, the lumped version of this thing would be 11.968. I'm going to do 97. So you can see we're rounding several times in here. Let's do the others. 14.88 times 0.9. That one's 13.39. And then 13.92 times 1.6. The last one is 22.27. All right, so the first thing that happens, start at 0. There's not a point load, there's a distributed load that is going to go down by 11.97, so down by 12, so it'll do something like that. And then we'll put our negative 11.97 there. And then we add, RB is pointing up, we add 29.8. So that gets us to 17.83. So maybe there. nothing happens until we get to the start of that distributed load over here. We lose 13.39, so minus 13.39. So we go down to 4, positive 4. So maybe right there, that's 4.44. And then there is a negative, this is easy to forget, but there's this negative point load there. So minus 8.48. We go directly down to negative 4.04. Uh-oh. Something didn't work out right. Let me check my numbers here. Or maybe I wrote something down wrong. Let me make sure I didn't write something down wrong. 13.92, 14.88. Hopefully I didn't write my reactions wrong. Let's see. I just copied them from here. It should be those two, 25.8, 30.3. Whoa, I did write that down. 25.8, I wrote 29.8. There we go, that's our problem. So, what happened was I was adding these numbers up and I wasn't going to get back to 0. I wasn't even going to be close to 0. And so I knew that somehow we had done something wrong. Turns out I wrote this down wrong. That's 25.8. So what that would do is that's going to change these numbers a little bit. So let's see. I go from the 11.97 is fine, negative 11.97. Then I would add 25.8, which would take me up to 30. I'm not going to reshape this. I mean, it's kind of close. Oh, it is going to go almost to 0, though. 13.83 minus 13.39 gets to 0.44. And now I subtract off another 8.48. And I go down to negative 8. So I go down a little bit further. Negative 8.04. And then I subtract off 22.27. Now we're looking much more like what we would expect. Call it right there, negative 30.31. Reaction at E is 30.3. Now I can say that that's probably right. And there's our shear diagram. It's got some interesting shapes in it. It looks like our maximum shear force is right there at the very end of the beam where the pin or whatever was at E. Roller, I don't know, it doesn't say, does it? It's just a reaction at E. So right there at the point at the right end of the beam is the worst case shear. Now we want to do the bending moment diagram. This one, remember, most of it comes by integrating the shear diagram. So this one does have all these concentrated moments, though, that we'll have to take into account. But let's go ahead and do our integrate the shear diagram. So I've got 11.97 times that's the height of this first triangle, times a base of 1.1 divided by 2, because it's a triangle, negative 6.58. Lots of rounding. The next one is 13.83 high plus 2 wide, and it's a rectangle. This is positive 15.83. This one is actually a very thin slice of a rectangle with a triangle on top of it. So the height of this triangle is 13.83 minus 0.44. So it's 13.39 high times 0.9 wide divided by 2 for a triangle. So the triangle part of this is 6.02 or 6.03. It looks like I'm only doing 2 decimals, so we'll keep with that. The square, well, not square, rectangle underneath this is 0.44 times 0.9. So we would add another little 0.39. I'll keep a third one this time because otherwise we just go to 0.4. Got the same kind of thing here, except it's negative. So this is 8.04 times 1.6, 12, negative 12.864. And then the height of this triangle is not 30, 30.31 minus 8.04. So it's 22.27 times 1.6 divided by 2 for the triangle, negative 17.816. Okay. Now we need us a zero line for our bending moment. Let's see. We're going to have some negative. It kind of goes both back and forth, negative and positive. So I'm going to kind of put it in the middle, right here. These will be units of kilonewton meters. Okay. Now what we need is we start at 0. This one instantly has moment 1 going around counterclockwise. So we haven't had many beams that have the concentrated moments on them when we were drawing shear and bending diagrams. That's kind of why I chose this one, even though it's got all this other stuff going on. It's so that we could have some practice putting concentrated moments into the moment diagram. So what we do is, if it is a counterclockwise moment, we subtract it. If it's a clockwise moment, we add it. External ones. So these are external bending moments, not internal bending moments. So the M1 is counterclockwise, so it's a minus, and it is 9.6. So we instantly go down. I guess we can count by tens again. That's probably fine. So this will be negative 10, negative 20, positive 10, positive 20. So we will go down. Let's see if we can get them all on here at the same time. That's probably as close as we can get. No, we can do that. All right, so this goes down, straight down, 9.6. So it goes down to right there. Negative 9.6. We'll put that kind of crowded right there. Then we've got a shear force that is increasingly negative. So that means our slope is getting steeper, but the negative part means that it's sloping downwards. So it generally has a negative slope, and it goes from this 9.6 that we're currently at, negative 9.6. We subtract off another, actually let me make that negative, negative 9.6 minus another 6.58. We go down to 16.18. So we go down here somewhere. And it starts at 0, the shear does. So that means the initial slope of our moment diagram is 0, which is horizontal. And then it curves more and more negative, something like that. And this number is negative 16.18. Then I have a positive shear, a constant positive shear. So that's a straight line. I'm at negative 16. I add 15.83. So that gets me to almost 0. So negative, I'm going to put that here, negative 0.35. And it's just a straight line because the shear in this section is constant. So practically to 0. Then it keeps going up a little bit more. So from the negative 0.35, I add 6.03 plus 0.396. So I'm adding that triangle and the little sliver of a rectangle. So I do peak over here at 6.076. And this one is, this one's different because I am getting closer to 0 but positive. So I have a slope that's pretty much the same here, and then it tapers off to go, I made this a little bit too small, so there's not a whole lot of curve going on there. It's hard to see that it's curved, but there is some curve. And then, oh, you know what? Undo. Because we forgot M2. This is the whole reason I wanted to do this particular problem. M2 is a concentrated moment that is clockwise. I think it's 3.2. I need to check and see. Yeah, 3.2 kilonewton meters. So when M2 comes into play, I'm currently at negative 0.35. And then M2 is clockwise, so it would be plus 3.2. So I go up, not a lot, but I go up. Oh wow, let's just draw it this way. 2.85. So that negative 3.5 is kind of in the way. We'll have to just erase it. This is 2.85. This number was that negative whatever, 0.34 or whatever it was. I don't remember what it was now. 3.5, I think it was. Okay. Now I'm at 2.85, positive 2.85. Now I can add plus 6.03 and 0.396. And I get all the way up to 9.276. Kind of like that. Then I have a negative, so minus 12.864, and then also minus 17.816. But that's, what's the moment at 3? Oh, something's still giving us problems here. Where is it? 3.2. M3 is 9.6. Oh, wait a second. This 15.83 doesn't look right, does it? I'm looking at, I'm checking the areas that we calculated for the shear diagram, the red numbers on the shear diagram. And first what I want to do is the 13.83, that should be times 2. B is 2. Yeah, and I don't know, oh, did I divide that by 2? Yes, I think I did. Or I wrote down some, I don't know where that number came from actually. 13.83 times 2 is 27.66. So that's, I mean, what we're going through here is good and bad. It's bad that I'm making this mistake, but it's good that you can kind of see what happens when you make a mistake. That's the good thing about the shear and bending moment diagram, is that they start and end at 0. So if you get to the end and you're off a little bit, you can say, well, that's probably I rounded. But I was going to be off again by quite a bit, and that's not rounding. And so that made me go back and check on this thing to see, and I actually want to check the other areas just to make sure that I didn't mess them up somehow. I'm checking the other ones right now. That one looks okay. 0.396. 12.864. Whoops, 30.31. Minus 8.04. Times 1.6 divided by 2. All right, all the other areas look okay. All right, so let's pick back up with, I believe the negative 16.18, that was okay. I believe that was okay. But we should add 27.66 to that, which would get us up to 11. Like there. Then we add 6.03 plus 0.396, another up to 17.906. Oh, I did it again. I forgot to add 3.2. So 11.48 plus 3.2, we go up to that little spot will be 14.68. for that peak right there. Then we add 6.03 plus 0.396. We get up to here, 21.106, and then hopefully these other two, the numbers look like they'll add to somewhere around there. So just checking. 21.1. We were at 14.68 plus 603 plus 0.396 minus 12.864 minus 17.816. Okay, so this one on the right hand side here, the total here, the 2930, whatever it is, will bring us from 21.106 down to negative 9.574. And it starts out, it crosses 0, and then it actually starts at negative 8. So it has a little bit of slope to it, but it gets more and more steep, so more and more negative. So it'll do something like this. And then M3 is 9.6. I'm at negative 9.57. I want to say that is rounding. So we got that one little weird blip at the end. But we finally have our bending moment diagram here. And we have two spots where we could think of the M max. So we have this spot, M equals negative 16.18 kilonewton meters. But we also have over here, M equals 21.106 kilonewton meters. Why I might want to keep track of both of them is that since one of these is negative and one is positive, that means that the beam is bending in opposite directions on those. So it might be, if I'm looking for a particular thing, like the maximum flexural stress or the maximum tensile stress, well, I meant compression or tension, not flexural. They're both flexural. If I want tension or compression, then it might mean that I need to go to one of these spots versus the other one. In this case, it doesn't, because this beam that we're trying to deal with is a wide flanged R American standard, so a WR and S. But either one of those, it doesn't matter. The distance from the neutral axis to the top and bottom is the same. If this was a T-shaped beam, the distance from the neutral axis to the top is shorter than the distance from the neutral axis to the bottom. And so they have different Y values that you would go in there depending on if you're trying to get to the top of the beam or the bottom of the beam. So if you wanted to know a particular thing, tension versus compression, it might be that you have a worst case scenario at one of these points versus the other one, just depending on the tension or compression you're trying to do. Anyway, we don't need that. We just need M max, hopefully. I wonder if we can check this. M max is 21.11 kilonewton meters. Now we've rounded many times between where we started and here, so I don't know how much WebWork is going to care for this. Well, there it is right there, the 21.09. That's our 21.11. So we did round enough to be off. WebWork probably is not happy with that. Let's see. Actually, it was okay. Maybe this problem has a little bit extra tolerance associated with it. All right, so what do we do with that? The problem is saying we want to find the lightest steel. So steel is just telling us the strength of the material. Wide flanged R American standard, so W, this is a W beam, and this is an S beam, so we have to look through both charts. That may be used for the beam shown if the maximum flexural stress must be limited to 74 megapascals. So remember, what we were trying to do is calculate our section modulus. So S equals, we use that right here, the maximum bending moment that our beam has to deal with, divided by the allowable stress. Now this one, they just told us the allowable stress, limited to 74 megapascals. So S is 21.11 kilonewton meters over 74 megapascals. Now we probably have to deal with these units here. We've got one in kilonewtons and one in megapascals. So I'm going to convert them both over to just Newton meter. So this will be 21,110 Newton meters over 74 times 10 to the 6th pascals, where a pascal is a Newton per meter squared. So you can always just remember that just by the stress equation for axial stress, force divided by cross-sectional area. So now if I divide these numbers, they'll come out in, S will come out in meters cubed. Now, that's fine, except that I think the chart is going to have it in like millimeters, but we'll deal with that once we get our number. So 21,110 divided by 74 million. So we get 2.853 times 10 to the negative 4th meters, not to the 4th, meters cubed. Okay. Now we need to find both of our charts for S and W. We're going to have to look in the exam reference for that, I think. I just don't know which one. There's some W's. All right, they're right there. So let's get this rotated the right way. Now, 10 to the 3rd millimeters cubed are what S is in. So we currently have it in meters cubed. So if I multiply times 1,000 cubed, so times 1,000 3 times, I will have this number, 285,270.3 millimeters cubed. That's not quite what they have here, though. They have millimeters cubed, but they have 10 to the 3rd millimeters cubed. So this number, 10 to the 3rd millimeters cubed, would be, this is a point, 285.27 times 10 to the 3rd millimeters cubed. So it's the 285 number that I'm looking for. So that's actually pretty large. Well, there's how they have it. There's the 285 that they have in here. They have it listed in meters cubed, which is right here, what we had earlier. But for the chart, we need it in 10 to the 3rd millimeters cubed. All right, so let's look at our charts. So we're looking for something greater than 285.27, and we're looking in the W's and the S's. So here are the S standard flange, and if you want to see the difference, here's the picture for the standard flange right here, and here is the picture for the wide flange over here. So you can kind of see how the flanges are wider on the wide flange. All right, it did not tell us anything that we need to worry with the YY direction, so we're only looking at XX. These are really big, so 285, it looks like the smallest one is this 408. So that is S254 by 38. Is there anything lighter than a 38 in this S column? No, there's not. So of the S beams, 254 by 38 works. So let's write that down. S254 by 38. It had a section modulus of, I don't remember, 408. Yeah, 408. But it also said, what about the wide flange beams? So let's look over here at the wide flange beams. And we'll look in the section modulus column. These are giant numbers. Let's see, where's something that's All right, so this 342 number is big enough. It is a 203 by 36, but let's look and see if there's anything lighter than 36. 46, 60, 30, there's a 33, that's lighter. Anything lighter than 33? 45, 39, no. So it looks like the contender here is 254 by 33. Oh wait, 380, what did we need? 280, okay. So that one will work. So 254 by 33. W, also 254, but 33, it had a section modulus of 380 something, 380. So it's not as strong, but it's strong enough for what we need because we only needed 285. So it's definitely more than that. It's not as strong as the 408 from the S-beam, but it is lighter, 33 versus 38. So we would choose this beam. And I think I saw that that's the one that they actually have listed here. Let's make sure. Yeah, 254 by 33. So that one took us a while, mainly because of the little things I kept doing wrong with our shear and bending diagram. On an exam, like I said, you're not going to have to go and draw the shear and bending diagram in order to do a design of beams. It's either going to be you start with this picture, so you've got all this stuff labeled on here, and you have to know to go find the maximum bending moment is basically all you need to know there. Or you have a problem statement like this, where it just gives you some, it gives you the maximum bending moment, tells you to go find the strength. Or it's one of these special cases where you don't have to draw the shear and bending diagram as long as you know that, oh, well, the maximum bending moment is just at the wall. I just solve for that. Or it's all symmetric. It's right in the middle. I solve for that. So that's one of those three cases. Or if I give you more than one beam design problem, which I usually don't. Usually there's only one. Then it's going to fall into one of those categories. Either it's just a shear and bending diagram where you go read off the diagram the number you need. It's a word problem, or it's a special case problem like one of these. So hopefully that gives you a little idea on what we mean by beam design. The only thing I can think of, let's see, no questions over there. So the only thing I can think of is if there's any confusion on when to use XX versus YY. That might be the only thing. I don't know that there is a problem set up that shows you a reason to use YY. I'm trying to look through. Actually, this one does. And not for the same reason though, but this is, you're just calculating a moment of inertia, so it is the same reason. But this is the cross section. I don't know how easily I can draw this picture, but just so that we have some idea of, I'm sure that you know why we're using YY versus XX. So here's our cross section, kind of like what they have. They made it out of some channel beam, actually a bunch of channel beams. So there's channel beams in here too. All right, so the ones in the middle, these, they're oriented where, and so you're assuming, let's skip too many steps here. You're assuming this beam looks something like this if we look at it in our sort of 3D way here. It's something like this. I don't know. So it's extruded into the page there a little bit. And the loads you're assuming are coming down from this direction on top of this beam, however they're loaded. So when we do that, let's go look at our channel C-section here. So there's the picture for which direction you use for XX and which direction you use for YY. And the flange, the ones that are on the top and bottom here that kind of make the flange of this kind of created I-beam thing, they're oriented so that the loads are perpendicular to the YY axis. The neutral axis of this guy, the neutral axis is through here, and the YY axis for the little flange on top is that direction. So this one is an example of when you would use the moment of inertia, not section modulus, but any data you were going to get for this top or bottom flange is going to be from the YY column. So if you want the moment of inertia, that's what you want in this particular problem. So if you want to work this one, it is, which one is it? Optional problem 16. It uses the YY axis. So if you want to try and figure out why you want to do that. Now, this one also does a different thing. This one is having you calculate two different moments of inertia. One about an x-axis that runs through the centroid. That's what the C means. So that would be, let me just copy this and make sure that this one isn't required, but this is a good problem to kind of practice with. So this ICX is the moment of inertia about the centroid of this shape, so the neutral axis. There would be ICX, or the moment of inertia about that axis. The other one is the moment of inertia about this axis. So it's got two different axes that it wants you to calculate the moment of inertia about. Speaking of that, on the exam, I can give you any axis on here. Calculate the moment of inertia about this axis. And I just call it my axis. You can calculate the moment of inertia. It's not the one that you would put into the flexural stress equation, but just for an academic, I'm going to calculate a moment of inertia problem, then you can pick any axis out there, or I can pick any axis out there and tell you to calculate the moment of inertia about that axis. You just basically treat it like you do the neutral axis. And it's just an academic test, basically. It's not thing that you'll put in the flexural stress equation, but it's a valid moment of inertia. It's just not for flexural stress. So I'm pretty sure there are going to be at least one problem, because if I don't give you a location for the neutral axis, that means you have to go find where the neutral axis is, and it's much simpler just to say, hey, here's an axis, it's 3 inches above the bottom, calculate the moment of inertia about that axis, versus you having to go find the location of the neutral axis and then calculate the moment of inertia. So that's the point of those particular problems. This one, I would say this one is a good practice one just for using the charts, figuring out the YY versus XX stuff. I would say this one's a good one to practice on. There's probably some in the homework also. I don't remember. I just usually look at the optional ones. They are optional, though. It's not required. All right. Still don't see any chat stuff. Only 4 people around, so I'm going to assume that everybody's good. And we will pick up next time with something. Let's see. Beam deflection, I assume. Yeah, there's 2 days of beam deflection. We're getting close to exam 2, kind of close to exam 2. Quiz 3 is open now. It's mostly frames and machine stuff. There's some concept questions on it. But it's got more questions, maybe 7 or 8 questions, but some of them are concepts, not calculations. So do that one relatively soon. And then we'll talk about this beam deflection, and that's the last topic for exam 2. Exam 2 will run frames and machines to beam deflection. And then we've got our last little set of things. And just so you know, this exam 1 or 2 redo, those are if for whatever reason you don't like your grade that you made on exam 1 or 2. Maybe you missed exam 1 or 2, so you have a 0. Or you just don't like the grade. You can retake either exam 1 or exam 2 and get a new grade for it. It's not the exact same test, but it's the same content, and it just replaces your new grade for whatever reason you might have. And then we'll do exam 3, which does cover everything, going all the way back to the beginning, so it is a cumulative type final, but there's probably half of it that is this new torsion and last little bits that we're going to cover at the very end. All right, I will see y'all Wednesday with some beam deflection.